In this video, we're going to discuss Bernoulli differential equations. We'll talk about how to recognize them, how to solve them, and then we'll work our first example. But before that, I want to review all of the methods that we've discussed so far regarding solving first order differential equations. That's what this unit is about. The first method that we learned was the method for separable differential equations. So we said that a differential equation is separable if it can be written in this form: dy dx equals a function of x times a function of y. If you can get y prime by itself, or the derivative by itself, and then factor the other side, then it's possible to separate the variables. Now, you don't always have to show this to show that it's separable. The idea is if you can algebraically manipulate your differential equation so that all the y's are on one side and all of the x's are on the other, and you have a function of y times dy on one side, and that's equal to a function of x times dx on the other, then it's separable. So for this one, I would divide both sides by g of y and multiply both sides by dx to get something that looks like this. Now I've got all x's on this side, all y's on this side, and to solve the differential equation, I just anti-differentiate. That'll get me an implicit solution, and if I want an explicit solution, I would just try to solve for y. Those are the simplest ones. And after we learned how to solve separable differential equations, we talked about first order, linear, ordinary differential equations, and the method of solving with an integrating factor. In this case, we said that if we had a differential equation of this form, or that can be written in this form, so we've got the derivative plus a function of your independent variable times your dependent variable equals a function of your independent variable. If the differential equation can be written in this form, this can be solved by computing what's called an integrating factor. The integrating factor is e to the integral of p of x power, and whenever we evaluate that antiderivative, we choose c to be 0. Then you're going to multiply the dE by the integrating factor, and it's at dE in this form, so I'm calling it dE star. And when you do that, the left-hand side will always be the derivative with respect to your independent variable of your dependent variable times your integrating factor. That was Bernoulli's brilliant idea. He said, if we multiply this guy by this, then the left-hand side will be the result of the product rule. It'll be the derivative of this product. We'll have the derivative of the first, that's this, times the second, the integrating factor will be there, plus the derivative of the integrating factor times the first will be this term times the integrating factor itself. And what's so brilliant about that is if we do that, if we multiply by this integrating factor and we recognize that the left-hand side is this, we're only 2 steps away from getting y by itself. All we have to do is undo this differentiation with anti-differentiation, excuse me, and then divide by the integrating factor. So it's a pretty simple method because you're just undoing operations. Although I will admit that the beginning of the method is not very intuitive at all. Most people don't look at this and think, oh, if I only multiplied by e to the integral of p of x dx power, then the left-hand side would be the result of the product rule, and then I'd be 2 steps from getting y by itself. Most people don't come up with that. Bernoulli came up with that. One of the Bernoullis came up with that. We did not have to come up with that. So I will admit that that first step isn't intuitive. That was Bernoulli's intuition. But now that we know that that first step gets us here, we can apply Bernoulli's method. So that's how we solve a first order linear ODE. If it happens to not be separable, I would always do this first because this is much easier than this. If it happens to not fall into this category, but the differential equation falls into this category, then you can solve it like this. Then after that, we talked about homogeneous polar differential equations. And we're using the word homogeneous here in a slightly different way than we were using it in earlier sections. And that's why I'm adding this word polar. Some differential equations textbooks don't use that word polar. These just call these homogeneous differential equations. And then they talk about a different kind of homogeneous differential equation in the other sections. But we're going to add that word polar to distinguish these from that other type of homogeneity. We said a differential equation is homogeneous polar if it can be written this way. If you can write dy dx as a function of y over x, then it's homogeneous polar. Or, there's another way to recognize it. If you can write dy dx as a function, as a quotient of two functions, g of x and y over h of x and y, where g and h are homogeneous functions of the same degree. Sometimes I hear people call this order rather than degree. If these are homogeneous functions of the same degree or the same order, then this function, this quotient, can be rewritten this way as a function of y over x only, or x over y, which is, just the reciprocal of that. If we're in this category or this category, and this one is equivalent to this and vice versa, then the differential equation is homogeneous polar. Now, just to remind you, function is homogeneous. It's homogeneous. It's a homogeneous function with degree n if the following is true. If replacing x with tx and replacing y with ty results in just t to the nth power times the original function. If you can do that, if you can just make that substitution and then factor out t to the n, then this function is called homogeneous and we say it has degree n. So these two functions have to be homogeneous functions and they have to have the same degree or the same order. If that's true, then this is solvable by letting v equal y over x. And if we let v equal y over x, there are certain consequences for dy dx. So dy dx is something that we can write in terms of v and x. And this f of y over x will be f of v by definition of v because we're letting v equal y over x. And then the resulting differential equation will be separable. So then we solve the separable differential equation, and it's separable in v and x, and then we just back substitute. So you're going to replace v with y over x when you're done. So that's that method. So when you look at this one on the surface, it's not separable initially, but through making this substitution, it turns out that it is separable. So we make a substitution, we solve the separable equation, and we back substitute. You're going to see there are a lot of differential equations that we solve in this class that after making a substitution turn into a separable differential equation, or after making a substitution will turn into a first order linear equation. So it's really critical that you learn these two methods because we're going to keep coming back to those over and over again. Okay, so we've got those two, and we've got the homogeneous polar DEs, and now we're going to learn this new method for Bernoulli DEs. And Bernoulli DEs are differential equations that are not first order linear equations, but after making a substitution, we can write them in a form that is first order linear. So we're going to do pretty much the same thing with Bernoulli equations that we did with homogeneous polar differential equations. We'll make a substitution, we'll write the equation in a different form. But then when the equation is in a different form, we're going to say, aha, look, it's first order linear. Then we're going to solve the first order linear equation and back substitute. So that's the idea behind the method for Bernoulli equations. Let me show you what a Bernoulli equation looks like. I'll put it at the end of this page. A differential equation is called a Bernoulli differential equation. if it can be written in this form, if you can write it as the derivative plus a function of your independent variable times your dependent variable equals a function of the independent variable times y to the n, that's the dependent variable to the nth power, where n is not 0 or 1. If you can do this, then this differential equation is called a Bernoulli differential equation. Notice if n were 0, I would just have a y to the 0, so it would be first order linear. Or if n were 1, well then I could just subtract f of x times y from both sides, and then it would still be first order linear. And it would actually be separable in the case where n equals 1. Yeah, it's going to be separable in that case. But if n is not 0 and it's not 1, we can solve this Bernoulli equation with the substitution that I'm about to recommend. So I'm not sure if it's the same Bernoulli. It's probably the same Bernoulli who came up with the method for solving first order linear differential equations. I'll have to get out some of my history of math books to see. But here's the idea behind the method. One of these Bernoullis said, try this for a Bernoulli differential equation. Let's let u equal y to the 1 minus n power. That's going to be our substitution. Then if that's true, the derivative of u with respect to x is the derivative of this with respect to y, because we're treating y as a function of x. Let's write that in here, where y is a function of x. The derivative of u with respect to x requires the chain rule, or you can think of it as implicit differentiation. I've got y to some power, and that power is just a number. The derivative of y to this power is that power times y to the 1 less power. And that 1 and the negative 1 reduce, and you just have a negative n there, times the derivative of the inside, that's dy dx. So let's simplify that a little bit. So you've got a constant times y to the negative n times dy dx. And that's the derivative of u with respect to x. Now, at this point, you're going to take your differential equation, your Bernoulli DE, which has to be written in this form. So I'm going to call this DE star. If it's not written in this form, you need to get it into this form first. So maybe that's the first step in the method, is to write the differential equation in this form. After you've written that differential equation in that form, I'm going to leave some space here. You want to take the differential equation. Oops, and there's a y to the n over here. And watch this. You're going to multiply both sides of the equation by this guy right here. Now, technically, that's the derivative of u with respect to y, but I'm not going to use that notation because it tends to confuse students. It's just that function. You're going to have a constant times y to some power, the function in front of the dy dx. That is what you need to multiply this by. So you're going to multiply every single term in your differential equation by that. And then watch what happens. By design, this piece is this piece. And that piece is du dx. So this first term will be the derivative of u with respect to x. And then watch what happens here. You've got a 1 minus n, which is just a constant, times p of x. So I'll bring my constant down. Oops. I'll bring my p of x down. And then what's left over? I've got a y to the negative n times a y to the first. Remember, you add the exponents. That's y to the 1 minus n. And that was our initial choice for u. So this times this, that becomes just a u. You multiply those guys together. That ends up with giving you a u right here. And then here's the beauty of Bernoulli. He said, multiply by this and watch what happens. That y to the n on the right-hand side, which made this Bernoulli rather than first order linear. When you multiply by that y to the negative n from that piece, those guys are going to be gone, and you're just going to have a constant times the original function from the other side. And don't get distracted by this. I know it makes it look more complicated, but this is just first order linear in u. You've got the first derivative of u with respect to x plus a function of x times u equals a function of x. I forgot to finish writing this out. We're multiplying dE star by 1 minus n times y to the negative n, which is that function from right there. And then you're going to simplify. And then you're here, I'm going to call this dE double star. Then this differential equation is linear in u. So then you're going to solve this linear equation for u. That's our third step. And to do that, you identify p of x, you take its antiderivative, you find the integrating factor, and so on. You multiply by the integrating factor, the left-hand side is the derivative of a product, and you take the antiderivative to get rid of the derivative, and you divide by the integrating factor, and eventually you get u by itself. So you solve the linear differential equation for u, and there's a lot of little steps involved that we studied already. But eventually you're going to do that. You're going to use the integrating factor method to isolate u. And then after you have solved the linear differential equation for u, you're going to back substitute. So you're going to have u equals something, and then you're going to replace u with y to the 1 minus n. So you're going to have y to the 1 minus n equals some function over here. And you're trying to get y by itself. So to get rid of this power, you're going to raise both sides to the 1 over 1 minus n power. Because that times that would give me a 1, and then you're going to have y by itself. Okay, so that was a really messy way to say this. Let me make it a little bit cleaner for you for your notes. Here's the method. I'm going to start by writing the DE in standard form. Standard form for a Bernoulli differential equation is this. You've got the derivative plus a function of your independent variable times your dependent variable equals a function of your dependent variable times y to the n, where n is not 0 and n is not 1. Then next, you want to identify n. So you just look at this equation, you say n equals 3, n equals 1/2, or whatever it is. And then you're going to let u equal y to the 1 minus n. Then you'll compute du. Or excuse me, not du. You're going to compute du dx, or the derivative of u with respect to the independent variable, whatever that happens to be. And if y is a function of x, and we're treating y as a function of x here, it says dy dx right there, so we know y depends on x. Then, according to the power rule, we get this. Bring that power down, multiply by y to the 1 less power, and then multiply by the derivative of the inside, which is dy dx. Then you're going to take your differential equation in standard form, and you're going to multiply by that piece. After you simplify, you should be able to write, well, it's not implies, sorry. After you simplify, you should be able to write the differential equation, the resulting differential equation, as a linear differential equation in U. where u is your independent variable instead of y. Then you're going to solve that differential equation. For u using an integrating factor. So you're going to use the integrating factor method that we talked about when we solved first order linear equations. Then you're going to back substitute. Again, that's just a replacement. You're going to replace u with y to the 1 minus n. And then you're going to isolate y. So whatever that power is, you're going to get rid of it. If that was y cubed, I'd take the cube root of both sides. So that's y to the 5th. I'm going to take both sides and raise it to the 1/5 power. Generally, you're just going to raise both sides to whatever power is necessary to make that a y to the 1st. So we can do that by raising both sides to the 1 over 1 minus n power. So if that's a 5, I'm going to raise both sides to the 1/5 power. If that's a 3, it's the 1/3 power. If that's a 3 halves, raise both sides to the 2/3. And that's going to allow us to get y by itself. Now this looks like a lot of steps, but it's really not too bad. What it is you're taking a differential equation, you see it as a Bernoulli equation, and you're saying, solve with this substitution. And then make the substitution. Then we're going to end up with a linear differential equation in u, and then we solve the linear equation in u, and we back substitute and solve for y. So it's just another substitution method that reduces a differential equation that can't be solved with the earlier methods to an equation that can be solved with the earlier methods. So making this substitution, we make it first order linear and we solve that equation instead. Okay, so that's the method. That's the messy first version of the method and why it works and how it works. Now let's work an example. This is a problem from the Nagel differential equations text. That is the official TCC text for differential equation at this time. This is problem number 23 from section 2.3. And I may be pronouncing your name incorrectly, Mr. Nagel, I'm sorry. And if you want to see the text, let me see, I got it right here. This is from this textbook, Fundamentals of Differential Equations. And there's another version of this that has that does not have the same chapters at the end. Like this is, I think, the long version. There's another one where this is yellow, and I think it might say Essentials of Differential Equations instead, or something like that. But yeah, both books are very similar. So that's where this problem came from. Now, it's not written in standard form yet, but notice you've got a y to the 1st here, you've got a dy dx, and you've got a y squared. The fact that there's a y squared there makes it nonlinear. But this kind of looks like a linear differential equation. That kind of looks like a piece of a linear differential equation. So I'm seeing Bernoulli in this. This is a Bernoulli differential equation. The first thing that we'll do to solve this Bernoulli differential equation is write the differential equation in standard form, or write the DE in the form dy dx plus a function of x times y equals a function of x times y to the n power. Well, in order to do that, I'll just subtract this guy from both sides. And I will call this DE star just to have a label for it. So I've got a function of x, and I'm factoring off that y, so it looks more like that. And this equals negative x squared times y squared. And that has the right form. The p of x is that negative 2 over x. The f of x is the negative x squared. And we've got a y to the second power over here. So that's the y to the n. So this is a Bernoulli differential equation with n equals 2. So now we're going to let let u equal y to the 1 minus n, and we'll compute the derivative of u with respect to the independent variable, which is x. So we're going to let u equal y to the 1 minus n, which is 2, so that's y to the negative 1. And then we compute du dx. The derivative of y to the negative 1 is negative y to the negative 2 times the derivative of the inside by the chain rule. Or you can think of it as implicit differentiation. If y depends on x, the derivative of inside is dy dx. So I'm going to take dE star, and I want this first term to be du dx when I'm done. So I'll take dE star and multiply both sides by this. That way, when I'm done, that first term is du dx by design. So we're going to multiply both sides by negative y to the negative 2, and then we'll simplify. So I'll have negative y to the negative 2 times dy dx. And then I still have minus 2 over x times y times negative y to the negative 2. Negative times a negative is positive. And that equals the negative x squared y squared times that negative y to the negative 2. Negative times a negative is positive again. Okay, and now we simplify. The y to the negative 2 and the y to the second, you add the exponents, you get y to the 0. So those guys are gone. All you end up with on the right-hand side is an x squared, which is good. Over here, this whole piece, that's du dx by design. So we're going to replace that with du dx. And then over here, we're adding 2 over x times y to the negative 2 times y to the first. Add the exponents, that's y to the negative 1. And what do you know? It's u. If you've done everything correctly, it will always be u. This piece times this piece, that's giving us that u right there. Okay, so we multiplied both sides by this coefficient, that negative y to the negative 2. And then we write the differential equation as a linear differential equation in u. And we've done it. So now we're here. Since it's linear in u, now we're going to solve the linear equation using that method for first order linear ODEs, which is the integrating factor method. So the first thing that we do with the integrating factor method is we identify P, we compute its antiderivative, and then we let the integrating factor be e to the integral of P of x dx power. So in our case, P is 2 over x. We want the antiderivative of that. That's 2 times natural log of the absolute value of x plus c. We don't need infinitely many integrating factors. We only need one of them. So we're going to choose c to be 0. And then the integrating factor is e to this power. Now, in order to simplify this, we're going to have to use some rules from algebra. Remember, if you've got a constant times natural log of a, you can bring that constant inside. That's the same as natural log of a to the n. So that 2 needs to go inside there, and I end up with e to the natural log of the absolute value of x squared. And now, because there's a coefficient of 1 in front of this logarithm, the e and the log undo each other. This is an exponential and a logarithm, and they have the same base. Those are inverse functions by definition, so it's just going to give us whatever's inside. So that's going to give us x squared, provided that x is not equal to 0. Because if x was equal to 0, we couldn't take the logarithm of that. Okay, so we found our integrating factor. It simplified to x squared. Now, whenever we're solving a first order linear differential equation, and that's what we're doing here, I'm going to call this DE double star just to have a label on it. We take that and we multiply by the integrating factor. So we're going to take DE double star and multiply by x squared. So I've got du dx here plus 2 over x times u equals x squared. And we're multiplying everything by x squared here. So this term gets multiplied by x squared, this term gets multiplied by x squared, and of course the right-hand side gets multiplied by x squared. And then of course we want to simplify. This x will reduce with one of those, so we end up with x squared times du dx plus 2x times u equals x squared times x squared, which is x to the 4th. Now, if we've done everything correctly, the left-hand side of this first order linear differential equation should be the derivative of the dependent variable, which is u, times the integrating factor, which was x squared. So we want to recognize the left-hand side as the derivative of u times the integrating factor. Now, let's check. This is a product. This is a function of x times a function of x. If I take the derivative of this product, I should get derivative of the first times the second. So that's that. Good. Plus the derivative of the second times the first. Derivative of the second is 2x, and we're multiplying by u, so we're good. So we've checked it out. It actually does equal what it's supposed to equal, and that's good. Now we're 2 steps away from getting u by itself. I want to get rid of this derivative, so I take the antiderivative of both sides with respect to x. And the antiderivative of the derivative is that original function. The antiderivative of x to the 4th requires the power rule. Add 1 to the exponent, divide by the new exponent. Don't forget your plus c. Actually, we use c for something else. I'll call this one c1. And I'm still 1 step away. I was 2 steps away from getting u by itself. Now I'm just 1 step away. Now I have to divide both sides by u squared to isolate u. I don't know if I said u squared or x squared just a second ago. Divide both sides by x squared is what I meant to say if I didn't say it correctly. You're just trying to get u by itself. So we had u times x squared equals 1/5 x to the 5th plus c1, and we'll divide everything by x squared. Now, if you want to, you can simplify that, dividing each of these terms by x squared. So I'll have 1/5 x to the 5th divided by x squared will be x cubed, because 2 of those will reduce. And then I have a c1 over x squared over here, or you could call that c1 times x to the -2 if you want to. So we've gotten u by itself, but remember, that was just, this variable u was just something that we made up so that we could solve a problem involving y. So we've got to go back to y. We made a substitution so that it would be first order linear, and we solved it. Now we need to go back to y. So we replace u with whatever it was in terms of y. In this case, it's y to the negative 1. And then you're just going to get y by itself. Now, a lot of students make the mistake here of taking each of these and thinking of them as fractions and flipping them, but that's not how it works. We have to flip this whole side and flip this whole side. So maybe I should have left it as that fraction. This is actually 1 over x to the 5th times x cubed plus c1 over x squared. That's my y. So we're raising, we replaced u with y to the negative 1, and then we solved for y by raising both sides to the negative 1 power. Y to the negative 1 to the negative 1 is y to the 1st. So that's our answer. But I don't like complex fractions. I don't like to have fractions within fractions. So I will multiply by the LCD. There's a 5 in that denominator and an x squared in that denominator. I'm going to multiply everything by 5x squared. That's legal as long as I also multiply the numerator of the larger fraction by 5x squared. That way I'm just multiplying the whole expression by 1. So I've got y as a function of x, and in the numerator it's 5x squared, and 5x squared times this piece. The 5's will reduce, we'll have x cubed times x squared is x to the 5th. And then the x squareds will reduce here, and c1 times 5 is just another constant. I'll call it c2. So that is our solution. It's simplified. And let's look at the method. Well, with the original differential equation, we see that x cannot be 0. So if I'm looking for an interval of existence, my interval cannot include x equals 0. And let's see, x can't be 0 there, x can't be 0 there. And I think that's the only issue. X can't be 0 there. And then, of course, x to the 5th plus c2 can't be 0. Because we can't divide by 0 in the end either when we take these reciprocals. So x to the 5th is not allowed to equal the negative of whatever that constant is. So x can't equal the 5th root of that negative constant. And the value of that constant is going to tell us what our interval is. If C2 is positive, so that this is the 5th root of a negative number, and then we end up with this negative 5th root of C2 over here, because the 5th root of a negative is a negative. Then the interval would be 0 to infinity, because this will be well defined as long as we're greater than 0. So that's a one possibility. Now if C2 is negative, so this is a negative times a negative, which makes that the 5th root of a positive number. In that case, this 5th root of a positive number is going to be over here. I know it still looks like it's a negative number, but if C2 is negative, a negative times a negative is a positive, and that's a positive number. In that case, our interval of existence would be the 5th root of negative C2 to infinity. Now those are finer points. It really just depends on the value of the constant. And the value of the constant is going to be determined by an initial condition. So in the absence of information, we can just say we're either in this camp or in this camp. And actually, when I look through this whole method, the issue was at 0. Well, it really just depends on what the initial condition is. This wouldn't even necessarily have to be positive. It could be negative infinity to 0. So there are lots of possibilities for that interval of existence. So that is our first example of solving a Bernoulli equation. Briefly go over the method. You write the differential equation in this form. Then you say, I'm going to identify n and let u equal y to the 1 minus n. Compute du dx using, however you prefer to look at it, the chain rule or implicit differentiation. That's going to give you a function of y times dy dx. Take your differential equation in standard form and multiply by that function of y. When you do, that leading term will become du dx by design, because that's what you chose to multiply by, so that first term was du dx. Then you're going to end up with a function of x times u, and you'll have a function of x over here if you've done all of your algebra correctly. If that does not happen, something happened up here. Maybe you chose the wrong value for n. Maybe you did n minus 1 instead of 1 minus n. But something happened if it doesn't reduce to a linear equation. Then it reduces to a linear equation if everything went well, if you did your algebra correctly. You solve the linear equation using the integrating factor method. You get u by itself, and then you back substitute. U is y to the 1 minus n. In this case, 1 minus n was negative 1. And then you raise both sides to the reciprocal power of whatever power is there. The idea is you want to raise both sides to 1 over this power, so that this times this gives you a y to the first. And remember, if you're taking the reciprocal of both sides, you have to flip the whole side. You can't just flip individual fractions. A lot of students on this problem have a tendency to make this mistake. They think that they have a over b plus c over d, and they're raising that to the negative 1. Sometimes they think that that's b over a plus d over c. They think they can just flip those separately and add them together. You can't do that. It's not legal. You could pick some values for a, b, c, and d and show that that's absolutely not what happens. Concrete examples tend to be excellent ways to understand and comprehend something that's a little bit more abstract like this. So make sure you do that. You get y by itself, and then you try to find that interval of existence if you can. So that's the Bernoulli method.